subjects of Q series today. All right, so the partition theorem, which I call as the Euler pentagonal numbers partition theorem, is the product is the generating function for partitions into distinct parts where we are looking at the parity of the number of parts. So if PD of n E and PDO of n denote the number of such partitions into distinct parts having an even and odd number of parts respectively, and if I split the set of partitions into distinct parts into two subsets in this fashion, that split is always the same except at the pentagonal numbers. Okay, so that's what the Euler's theorem is in terms of a partition identity. Okay, so the generating function for partitions into distinct parts is this product 1 plus q to the power of m. But if I want to count parts with the frequency of occurrence of the number of parts, I can put a parameter z, and then that is PD and k, the number of partitions of n having k distinct parts. The number of distinct parts is k. So then we have that. All right, now there is one more theorem of Euler with which one usually starts the subject. There are so many theorems in the theory of partitions due to Euler, but this is often called Euler's theorem. This says that if you look at partitions into distinct parts, they are equinumerous with partitions into odd parts. This is probably the first theorem one learns in the subject, and it involves a little trick, a trick that actually dominates the subject, meaning it comes in several instances. So the generating function for the partitions into distinct parts is this. I replace 1 plus x by 1 minus x squared over 1 minus x, and I get the, after cancellation, the generating function for partitions into odd parts. Since I said it dominates the subject, I'm just going to make a one-line reference to a former student of Professor Lepowski, Caparelli. His partition theorems could be either stated as mod 12 partition theorems or mod 6 partition theorems, and precisely it is the Euler trick that converts the 6 to the 12. So this sort of thing comes up in the subject quite often. So simple as it is, it actually shows up in many instances. So now comes a question. Partitions into distinct parts are equinumerous with partitions into odd parts. And partitions into distinct parts can be split into two subsets so nicely. So should one ask the question that partitions into odd parts should also have some way of being split into two subsets? Well, the first person to consider this was Nathan Fine. And this happened in the middle part of the 20th century. So, and I think this is one of the reasons is people did not always look at the combinatorial aspect of the Euler identities. Okay, so here is Nathan Fine's theorem. Very pretty theorem, but this is a mid-20th century theorem. Okay, so many years after Euler. You take partitions of n into distinct parts, and now you look at the largest part. Now the largest part could either be odd or even, so you classify according to the parity of the largest part. That's your QA of n. Next, you look at partitions of a number into odd parts. Now you don't look at the number of parts, because an even number will have an even number of odd parts, and an odd number will have an odd number of odd parts. That's not interesting. But now if you look at the largest part, you can ask whether the largest part is 1 mod 4 or 3 mod 4. You classify according to this. And Fine's observation is that when you look at the parity difference, this is always 0 except at the pentagonal numbers. To me, it is very surprising that this theorem was never stated explicitly until Fine did so in the middle of the 20th century. I mean, it's just mind-boggling to me. So many people working, Sylvester or everybody else. What a fine companion to Euler's pentagonal numbers theorem. The only point here is, if one puts emphasis on theta series, the signs here are wrong. So this is, you're not getting an actual theta series. You're going to get what is called a false theta series. Okay? So let me just talk about the analytic form of Fine's theorem. So the analytic form of Fine's theorem is given here. So just for this one I've written. And so here is what you get is your false theta series. You get your pentagonal numbers, but the signs are all mixed up. By the way, George Andrews has said, and rightly so, that when Ramanujan wrote this letter to Hardy and said he has discovered these magnificent objects called the Mach theta functions, so they are truly magnificent objects, he also put in this statement, these come in much more naturally in the theory than the false theta functions discovered by Professor L.J. Rogers. Well, for this and for other reasons, false theta functions have not received the recognition that is due. They are sort of lesser status compared to the theta functions, the Mach theta functions. But they are just as beautiful from a combinatorial point of view. All right, so this is just the standard notation that we all use in the theory of hypergeometric series. So I'm just putting this up for sake of completeness. But now I want to say something else. Since I mentioned Ramanujan, I want to say Fine's theorems were actually implicit in Ramanujan's last notebook, as we have now realized. So this is a pair of identities in Ramanujan's last notebook. And it turns out that if I dilate Q by Q squared, the